In this video, we're going to continue our discussion of power series functions. Exercise 1-A. Express the function f of x is equal to log of 1 plus x divided by 1 minus 2x as a power series and find the radius of convergence. Exercise 1-B. Express f of 1/4 as a sum of an infinite series by using the result of exercise 1-A. Exercise 1C. Can we express f of 3/4 as a sum of an infinite series? Let's look at part A first. Notice that the derivative ddx of log of 1 plus x is equal to 1 over 1 plus x. So let's rewrite the function f of x is equal to log of 1 plus x divided by 1 minus 2x. Let's apply the property of log, so we get log of 1 plus x minus log of 1 minus 2x. So the property of logs is log of a over b. When you're dividing, we subtract. Log of a over b is equal to log a minus log b. Now, we have log of 1 plus 2x, we have log of 1 plus x divided by 1 minus 2x. We would like to write this as integral of a geometric sum. So we can write this as integral of 1 over 1 plus x dx, because the antiderivative of 1 over 1 plus x gives us log of 1 plus x. Now, let's look at this part here. What should we integrate to get log of 1 minus 2x? So let's try 1 over 1 minus 2x dx. If we integrate this, we get log of 1 minus 2x divided by minus 2 because of the U substitution rule. Because if you let u be equal to 1 minus 2x, du is equal to negative 2 dx, U substitution. U sub. For that reason, we're going to put negative 2 in the front to compensate. So now we've written the function as the integral of the sum of two different geometric series. So we can rewrite this. Let's clean it up a bit. We get integral 1 over 1 minus x dx. Minus times minus gives us plus 2. Integral 1 over 1 minus 2x dx. So now that we have written both integrands as the sum of a geometric series 1 over 1 minus r is equal to summation n equals 0 to infinity r to the power of n, and the radius of convergence is 1 for a geometric series, so absolute value of r less than 1. We can expand this sum and integrate term by term to get the power series representation of this function. So the key idea was to write this function as the integral of a sum of a geometric series, then write it in this way so we can define the common ratio. For the first integrand, the common ratio is minus x. For the second integrand, the common ratio is 2x. All right, so we've written log of 1 plus x divided by 1 minus 2x as the integral of 1 over 1 minus x dx plus 2 times integral 1 over 1 minus 2x dx. So what we get is, we get integral of 1 over 1 minus x, so that's integral summation n equals 0 to infinity minus x, which is a common ratio, to the power of n dx plus 2 times integral summation n equals 0 to infinity 2x to the power of n dx. Let's simplify this a little bit. We get summation, we get integral summation n equals 0 to infinity minus x to the power of n can be written as minus 1 to the power of n x to the n dx plus 2 times integral summation n equals 0 to infinity, and 2x to the power of n can be written as 2 to the power of n x to the power of n dx. All right, now integral of a sum is sum of the integrals. So we can write this as summation n equals 0 to infinity. We can put negative 1 to the power of n in front of the integral. And we integrate the part that involves x, integral of x to the n dx. Now this 2 is a constant. It passes right through the integral, so we can bring it inside this summation and multiply by 2 to the power of n. We have the same base, so they add up and we get 2 to the power of n plus 1. So we have summation n equals 0 to infinity. Integral of a sum is sum of the integrals. 2 to the power of n plus 1, this is a constant. It stays in the front of the integral. And we integrate the part that involves x. We're integrating with respect to x. All right, let's do the integration. So we have summation n equals 0 to infinity minus 1 to the power of n, x to the power of n plus 1 divided by n plus 1 plus summation n equals 0 to infinity 2 to the power of n plus 1. And we integrate x to the power of n, we get x to the power of n plus 1 divided by n plus 1 plus constant of integration plus c. Now let's group these two summations as one summation. So we have summation n equals 0 to infinity. Let's look for a common factor. What is a common factor? This part, x to the power of n plus 1 divided by n plus 1, and x to the power of n plus 1 divided by n plus 1 for the second summation as well. So we can write this as x to the power of n plus 1 divided by n plus 1. That's a common factor. So we get negative 1 to the power of n plus 2 to the power of n plus 1. And now we've grouped these two summations as one summation. So we've simplified it quite a bit. So this is in fact the power series representation of this function. F of x is equal to log of 1 plus x divided by 1 minus 2x. Let's write this in on the side here. Log of 1 plus x divided by 1 minus 2x. All right, let's find the constant c. So we have log of 1 plus x divided by 1 minus 2x is equal to summation n equals 0 to infinity, negative 1 to the power of n plus 2 to the power of n plus 1 divided by n plus 1 times x to the power of n plus 1 plus c. How do we solve for the constant c? The easiest way to do that is to plug in x equals 0 into both sides of the equation. Plug x equals 0 into both sides. Now plugging x equals 0 into the left-hand side gives us log of 1 plus 0 divided by 1 minus 0. Plugging x equals 0 into the right-hand side gives us summation n equals 0 to infinity minus 1 to the power of n plus 2 to the power of n plus 1, 0 to the power of n plus 1 divided by n plus 1. Plus c. Now, every term of this summation will be 0 because we're multiplying by 0. 0 to the power of n plus 1 is just 0. So on the left-hand side, we get log of 1. What is log of 1? Log of 1 is, of course, 0. So on the left-hand side, we get 0. On the right-hand side, this entire summation collapses to 0. So 0 plus c. That means the constant of integration, the arbitrary constant of integration, c is equal to 0. So we now have found the power series representation of the function log of 1 plus x divided by 1 minus 2x is equal to summation n equals 0 to infinity minus 1 to the power of n plus 2 to the power of n plus 1. We've written it in a compact notation, x to the power of n plus 1 divided by n plus 1. Now let's find the radius of convergence of the power series of f of x is equal to log of 1 plus x divided by 1 minus 2x. That means we want to find the values of x for which this power series representation represents this function. So first we'll find the radius, then we'll find the interval of convergence. All right, now let's look at the function log of 1 plus x divided by 1 minus 2x. Notice we wrote this as the integral of the sum of two different geometric series. This part was log of 1 plus x, and this part was for log of 1 minus 2x. Now let's look at the integrand. The first integrand, this is this part here, 1 over 1 minus x, is a sum of a geometric series with common ratio r equals negative x, and converges for absolute value of minus x less than 1. That implies it converges for absolute value of x is less than 1, so the radius of convergence for log of 1 plus x is just equal to 1. Radius is equal to 1. The second integrand, 1 over 1 minus 2x, this part here, is the sum of a geometric series with common ratio r equals 2x, and converges for absolute value of common ratio less than 1, absolute value of 2x less than 1. Divide by 2 both sides, that means absolute value of x less than 1/2. Therefore, the radius of convergence is equal to 1/2 for log of 1 minus 2x. Now, this is very important. We're adding these two power series. We should take the minimum of the two values of the radius. So radius will be the minimum of 1/2 and 1, and of course the minimum of these two numbers is 1/2. Always take the smaller value of the radius if you're adding two different power series, because it has to work for both of them. All right, so what we have is log of 1 plus x divided by 1 minus 2x is equal to summation n equals 0 to infinity, negative 1 to the power of n plus 2 to the power of n plus 1 times x to the power of n plus 1 divided by n plus 1. The radius of convergence, r, is equal to 1/2. We found that. And the interval of convergence, the values of x for which this power series represents this function, is x less than 1/2, larger than negative 1/2. Now here we have the expanded version of this power series just by plugging n equals 0, n equals 1. So this would be plugging n equals 0. This term is obtained by plugging n equals 0. This term is obtained by plugging n equals 1, n equals 2, n equals 3, and it goes on forever, as it's an infinite geometry, is an infinite power series. All right, so this is the expanded form of the power series. We're going to need it for the next section. So here we have express f of 1/4 as the sum of an infinite series. So that's what we have to do for this question. Well, all we have to do is plug in x equals 1/4 into the power series for f of x is equal to log of 1 plus x divided by 1 minus 2x. We found this power series. The power series is summation n equals 0 to infinity minus 1 to the power of n plus 2 to the power of n plus 1 x to the power of n plus 1 divided by n plus 1. For absolute value of x less than 1/2. The radius of convergence is 1/2. Now, what allows us to plug x equals 1/4 in? The reason is because x equals 1/4 is inside the interval of convergence, x less than 1/2, larger than negative 1/2. That means we can find the sum. So f of 1/4 is equal to log of, plug x equals 1/4, we get 1 plus 1/4 divided by 1 minus 2 times 1/4. Simplify that, we get 5 over 2. Log of 5 over 2, this is equal to summation n equals 0 to infinity minus 1 to the power of n plus 2 to the power of n plus 1 times 1/4 to the power of n plus 1. Let me separate this, put this in a circle, and divided by n plus 1. Now, there's a key concept here, and we should emphasize this. X equals 1/4, the value of x that we're plugging in is inside the interval of convergence. Inside the interval of convergence. And the interval convergence is negative 1/2, comma 1/2. X equals 1/4 is inside the interval, so that means we can simply plug in x equals 1/4 and get the sum of the power series. So f of 1/4, plugging x equals 1/4 into here for x, this is equal to log of 5/2, log of 5 over 2. This is equal to, now let's use the expanded version that we had earlier, plugging x equals 1/4 in every term. So we're going to get 3 times 1/4 plus 3/2 times 1/4 squared plus 3 times 1/4 cubed, and so on. Alright, so this is an infinite series, and the sum of this infinite series is equal to log of 5 over 2. Now, let's look at part C. Can we express f of 3/4 as a sum of an infinite series? The answer is no. And why is that? We cannot plug x equals 3/4 into the power series for f of x is equal to log of 1 plus x divided by 1 minus 2x, because x equals 3/4 is outside the interval of convergence, outside the interval of convergence. The interval of convergence is, of course, x less than 1/2, larger than negative 1/2. Let's draw it on a number line. Here is 1/2. Here's the origin, 0. Here's negative 1/2. And negative 1/2, let me write this as, there's negative 1/2 here. And 3/4 is here. It's outside. The interval of convergence is between negative 1/2 and 1/2. But 3/4 is outside the interval of convergence. Notice in the previous case, we were able to plug x equals 1/4 into the power series representation of this function log of 1 plus x divided by 1 minus 2x, because 1/4 was inside the interval of convergence. X equals 1/4 was inside. But x equals 3/4, x equals, let me write that, x equals 3/4 is outside the interval of convergence. All right, thanks.